Hi, this is Maggie. In this video, we're going to solve a programming problem using the set and dictionary data structures in Python. Before we get started, I'm going to quickly give you some tips for how to get the most out of this video. First, if you have problem solving with Python, read up through Chapter 8. If you don't have it, you can still learn a lot from this video. Open up idle and follow along with Python as I work. Sometimes I'm going to suggest you pause the video and complete some steps on your own. When I do that, pause the video and do your best to complete the steps on your own. The way to learn to program is by programming. You can watch and learn if you work along with me. Remember, you can always pause the video and try something, or go back and watch again. You don't have to wait for me to tell you to pause. There are some automated exercises in the description of this video. The exercises work with the same code or similar code to the code in the video. After you've completed the video, try the exercises to cement the concepts in your mind. Now let's get started. The problem we're going to solve is very well defined. We're going to create a text version of a wordle game. We're not going to create a complete wordle game, but we're going to figure out how to store and manipulate the words and guesses, and look at how Python data structures can make the problem a relatively easy one. To start, I'm going to play a version of Wordle that I wrote with Pygame, so you know how it works in case you haven't played the game before. And mine isn't as nice to look at as the ones you'll find online, but it has some interface features that the ones online don't have. That's not our focus, though. So first, before we start, Wordle has chosen a 5-letter English language word for me to guess. I have to guess it. The principle is like Mastermind, if you've ever played that. I put in a guess. Let me show you first that it won't tolerate a nonsense word. I'll type 5 Ds and then press enter, and it's basically ignoring my guess. So let me put in an authentic guess. I'll guess hello. Okay, now Wordle gives me hints. It marks a letter in yellow if it's in the word, but I have it in the wrong place. If letters are gray, they're not in the word. And down at the bottom, there's a list of all of the letters, and it's colored them the same as in my guess. So let me try another word with an H in a different place and different letters. I'll try winch and press enter. And I've learned 4 more letters that aren't in the word. And I've learned that H isn't at the end either. So let's try something that starts with SH. How about shark? Oh, good. And we get the first 3 letters correct and in the correct places. Now we need to figure out a word that begins with SHA and doesn't include any of the eliminated letters. We have 6 guesses total. Okay, and it's not shady. And it's not shaft. I have one more guess, and I have no idea. The problem with my game is I got a word set from the internet, and it includes words that are extremely obscure. The real game allows you to guess obscure words because they are real words, but it chooses the puzzle words from a smaller set of more common words. If I run the game again and print the word, I'll be able to see what it is. It'll be the same word because the game chooses a new word every day, just like the real game. Okay, and it's shama, which is not a word I've heard. That's okay. Hopefully that was a good enough problem specification, since we're imitating a program that already exists. Ours won't be a complete game or have a graphical user interface, though. We'll just figure out how to store the words, how to check a user guess against the word list to make sure it's a real word, and how to figure out what letters are in the right place and what letters are in the word but in the wrong place. This is a little trickier than it might initially seem because some letters can be in a word twice, but it's a great problem to solve with sets. Let's begin by loading the words into a list. The words that I got off the internet are in a text file, 1 word to a line. This should be pretty easy. Let's write a function that will take the file name as a parameter and will return the list of words as long as that's a real file, and will otherwise return the empty list. Why don't you practice your file reading and lists by writing this function? Pause the video and write a function that takes the file name as a parameter, checks that the file exists, and then opens it and reads the contents into a list. The contents is 5-letter words, 1 to a line. Pause now. How'd you do? So here's what I have. First, I import OSPath and typing. My function is called readWords, and it takes file name, a string, as a parameter, and it returns a list. I've written a docstring, open file name, and read the words in it to a list. Words are organized in the file 1 to a line. Return the list, or the empty list, if there is an error with the file. And then I've annotated file of type typing.txt.io, and words, a list, and initialized that to the empty list. Then I wrote if os.path.isFile and pass file name as a parameter. And if that's true, then I open the file, use readlines to read the file into the list called words, and close the file. At the end of the function, I return the list words. In the main module, I invoke this function and print the word at index 0. And when I run it, it prints women. Okay, so we have a list of words. Now, we want to do two things with the list, basically. We want to get a word out of it to be today's puzzle, and we want to use it to check if the word entered by the user is a real word. We're not going to worry about pulling out a word based on the date, which is how the real Wordle works and how I wrote my own Wordle program, because that's not relevant to our topic. So we could just hard-code an index to grab a word or randomly choose a word. Checking the user's word against our word list to confirm it's a real word is relevant. How long is our list? Let's change the program to store the result of read words in a variable and then print the length of the list. And I'll run it. Okay, 12,947. That's a pretty long list. Let's use in to check if the word DDDDD is in the list. It shouldn't be. It prints false. Now, a list is a good data structure if we're going to be adding and removing elements as the program is executing, and if there might be duplicate elements. But that's not the case with this data. Each word in the list is unique, and the list isn't going to change while the program is running. So we can use a more efficient data type for this. We can use a set. And as an example of a set's efficiency, let's import time at the top of the program, and then use time.perf_counter_ns, which we can use to measure elapsed time in nanoseconds. I'll set old time int equal to time.perf_counter_ns, and after that, simply check DD in words. It isn't. So that will require checking it against all of the words in the list. And then I'll set new time equal to time.perf_counter_ns and print out the difference between old time and new time. That will tell us how many nanoseconds that operation took. I'll then create a set S from the words by writing S set equals set words, and then I'll do the same thing and print the difference. Let's run the program and see what the two times are. Okay, and for this example, using in with a set is faster than using in with a list. But because of the way sets are stored, as the list gets larger, the search on the list will take more time. The time will increase linearly with the length of the list. But the search on the same sized set will take the same amount of time. I ran an experiment in which I increased the size of the list by 10 times, and the list search took almost 10 times as long. The set search took exactly the same amount of time, regardless of size. So sets are efficiently stored for searching, meaning a set is a good choice for storing our list of words so we can check if a word that the user typed is an actual word. And we can use in to do that. That's one part of the problem now that we know how to solve easily and quickly. The trickier part of a Wordle game is offering the user clues. We need to tell the user which letters in their word are not in the puzzle word, which letters in their word are in the puzzle word in the correct location, and which letters in their word are in the puzzle word but not in the correct location. If there were only one of each letter per word, this would be a little easier. but there is the possibility of duplicate letters, such as in the word sieve. If the user guesses rinse, they've guessed E in one of its correct locations, and we don't want to tell them they've guessed E but in the incorrect location, even though there is another E in the puzzle word in a different location. Now, I thought about how to solve this for a while. I didn't want to look up how other people had written Wordle games. I really wanted to think about what tools I had at my disposal and solve the problem in an efficient way. A hint to you is that I decided to use sets to solve this problem, or part of it. Now, you might think of a better way to solve the problem, but what you're going to see here is a solution with sets. Pause the video and think about the problem. Come up with as many different examples as you can, such as the user's guess has no letters in common with the puzzle word. It has all letters in common in the wrong locations. All letters in common in the right locations. Duplicate letters in correct and incorrect locations, etc. Pause and see what you come up with as a solution to offering the user accurate clues. Pause now. So how did you do? Did you come up with a solution? I'm going to tell you about my solution, but as I mentioned, you may have come up with a better one. I really like programming solutions that are mathematically based. Those solutions are generally more elegant because math operations are accurate, and math was invented to solve real-world problems, so it's logical to look for the mathematical solution that applies to a problem we have because that math was designed to solve problems like that. For the Wordle problem, the problem with sets is that there are no duplicates allowed in a set. So we can't take a word, like sieve, and represent each individual letter in the set because we'll lose our second E. But that's not good enough anyway, because we also need to represent the locations of the letters. So I decided to construct ordered pairs of index letter from the puzzle word and the user's guess. Let's pretend sieve is our puzzle word. Then the set of ordered pairs would be 0S, 1I, 2E, 3V, 4E. Each one will be unique, even if the letters aren't, because the positions are unique. Now, just speaking theoretically, if I construct a similar ordered pair from my guess word, rinse, well, let me give you the opportunity to do that. Pause the video and construct a set of ordered pairs of the guess word, rinse, and compare it to the set of ordered pairs of the puzzle word, sieve, and think about the set operations, union, intersection, and difference, and see if you could find a way to give the user accurate clues about their guess relative to the puzzle word. Pause now. How'd you do with that? Let's create the set of ordered pairs for rinse. We have 0R, 1I, 2N, 3S, 4E. So, what operations might be useful here to give our player clues? Well, hopefully you noticed that if we compute an intersection, we get all of the letters that are in the correct location in the word. In this case, that's 1I and 4E. We can then remove the intersection from both sets using difference. Now what we have left of our guess word is either letters in the wrong location or letters in the guess that aren't in the puzzle word. At this point, we can lose our ordered pairs and return to lists of letters, so we can have duplicates and use in to test whether each letter in our guess is in the puzzle word, remove it from both if it is, and remove it from our guess word if it isn't, considering it a dead letter. Now that I've gone through my algorithm, pause the video and see if you can program it, particularly the set manipulations. Just accumulate the parts of the guess word into 3 different lists as your result. Ordered pairs of location, comma, letter in the word in the right location, just letters in the word in the wrong location, and letters not in the word. I'll do the same, and we'll compare when you come back. Pause now. How did that go? Let me first run my program so you can see what the output looks like. And then if that sparks some insight into what we're doing, maybe you'll want to pause and try again if you didn't quite get it. So I'll run the program, and it asks for my guess, and I'll say rinse. I've set the puzzle word to sieve as in our example. And the output is letters in the correct location, 1I, 4E. Letters in the word in the wrong location, S. Letters not in the word, NR. Okay, and to do this, I've written a number of small functions. This one, getWord, is really a stub. It returns a string which would be the puzzle word, but I've just hard-coded our word sieve. We know that we could read in the list and choose a word from our list based on the date. And the next function, getUserWord, just prompts the user for a word and then returns the first 5 letters of the word in case the user typed more than 5 characters by accident. Now we could also check that the word is a word here and use a loop to prompt the user until they give us a word. If I were going to write the function that way, I'd read in the word list elsewhere and pass it in as a set, and use in to check the word in an input validation loop. And then the next 2 functions convert a list of letters to a set of ordered pairs of location letter, and converts a set of ordered pairs of location letter back to a list of letters. So let's look at each of those. The first converts a word, a string, to a list of ordered pairs. Def word to ordered pairs, word string returns a set, then a docstring, return the word as a set of ordered pairs of tuples of letter, comma, index. I declare a few variables. I for the index of the letter, a string for each individual letter in the word, and result, a list. I start with a list because sets are immutable. So I'm going to create a list and then convert it to a set before I return it. Then for letter in word, result.append, and I pass in the tuple I, comma, letter, I plus equals 1, and then return set result. And to convert back, def pairs to letter list, pairs set, returns a list. Take a set of ordered pairs and convert to a list of letters. Letters, a list, is initialized to the empty list. And then for each ordered pair in pairs, I append to letters pair sub 1, which is the letter in the ordered pair. And I return the list of letters. Okay, now the main function is where we put it all together. So first, I just get the puzzle word and convert it to a set, and then get the user guess and convert it to a set. Now here's the set manipulation part, in which we find all of the letters that are in the correct location and remove them from both sets. And it's so easy. We just use intersection, which is the ampersand, and I store that intersection in the variable green letters, because that's the color in Wordle for letters in the correct location. And then for the rest of the puzzle and the rest of the guess, I use set difference, the subtraction operator, to remove the green letters from each of the original sets. I then convert those back to lists of letters. Now I create 2 empty lists, one for the letters not in the word, and one for the letters in the word but in the wrong location, and iterate over the letters in the guess, checking to see if they're in the word. If they're in the puzzle word, I remove them from the puzzle word and store them in the wrong location list. If they're not, then I just store them in the not in word list. And then I print everything out. So it's pretty straightforward once we've removed the letters that are in the correct location. And this will work with duplicate letters, as with the 2 E's in sieve. We found the E in the right location, but let's try another guess with 2 E's. Let's try teams. It correctly identifies the E that is in the right location, but it also identifies that there's an E that's in the wrong location. Or suppose we put both E's in the wrong location, as in 7. It correctly identifies the 2 E's and the V as being in the wrong location, but in the word. Okay, now we got to play with sets a little, but we didn't get to use a dictionary. So suppose you want to store a list of puzzles that you solved in 1 guess, in 2 guesses, in 3 guesses, etc. That would be a perfect application for a dict. Let's hardcode one and see how it would work. Now, just opening up the list of words and looking at the first few that I think are actually words, because this is a crazy list. So I'm going to write scores equals open curly brace 1 colon open close square brackets 2 colon women cabin 3 colon sable worth 4 colon pixie 5 colon empty list 6 colon empty list. Made a mistake with a brace in there. There we go. And maybe we'd want to store words that we didn't get in 6 guesses too. Maybe that would be another dictionary key, such as 7, because once you miss your 6th guess, you don't get any more guesses. So if I then query it, scores 3, I'll get the list sable worth, which is a list of all of the 3 guess words. In practice, since there's only 1 word per day and you might run your program, play, and then close it, this is another data structure you'd want to write out to disk. But let's imagine how it would work without worrying about the file part. Pause the video and think about how you'd construct this dictionary and how you'd add to it. Say the user played the game and they scored a 4 on the word sieve. How would you add that to the dictionary? Pause now. How'd you do? Now, you could certainly hardcode this dictionary or create a literal dictionary of empty lists like I did when I showed you what a dictionary like this might look like. Or you could use a loop and iterate over the keys of the dictionary 1 through 6 or 1 through 7 and set each value to the empty list. Or, and I think this is the best solution, you could use a default dict. Remember, for a default dict, which has list values, this will automatically create an empty list for any new key, and we can then simply append to it without having to check to see if the key is already in the dictionary, so we don't need to create the initial dictionary value. When we want to append to the value for a particular key, we can just append. If there's a list there, we'll be appending to the list. And if there isn't a list there, Python will use the empty list and we can append to that. So in my example, I've imported default dict from collections. Then in my main function, to demonstrate how this works, I've annotated and created a variable called scores of type default dict with value type list. I then append the string sieve to scores sub 4. I print scores, and I also print scores sub 4 and scores sub 2. And then I print scores again. Let's run it. And we can see the entire dictionary, which shows us just the key 4 and the value, a list, consisting of the string sieve. And then, remember, we print scores 4, which is sieve, and then I print scores 2, which is the empty list because that's the default value. Then, when I print scores again, it shows entries for both 2 and 4 because I accessed entry 2, which created it in the dictionary. So that's an illustration of how we might use dictionaries, sets, and of course lists in the solution to the problem of creating a wordle game. To practice with this, I recommend you rewrite what I've written here, as always. There are also practice exercises in the description that will go through the same code. Once that makes sense, wrap some more of a program around it. Let the user guess the word up to 6 times and report the green, yellow, and gray letters each time. Make sure you tell them if they've won and don't give them more guesses if they've won. Store their result in the dictionary. Maybe wrap the whole game in a loop that lets them play as many times as they like and shows them the list of words associated with each score at the end. Of course, you can come up with your own variations. Have fun with it.